Okay, so let's go over the answers on this. Hopefully you gave this a good attempt. So letter C, an Olympic diver slows down after splashing into the water. So he's moving down, and he's going to slow down, so his acceleration vector is upwards. D, a southward bound free kick delivered by the opposing team is slowed down and stopped by the goalie. I think it should be say free kick, by the way. So a southbound, it's moving southbound and it's slowed down. So the direction of the acceleration vector is north. E, a downward falling parachutist pulls the cord and rapidly slows down. So he's moving down, he's slowing down, so his direction of acceleration is up. Letter F, a rightward moving Hot Wheels car slows to a stop. So he's moving to the right and he's slowing down, so the acceleration vector is to the left. Letter G, a falling bungee jumper slows down as she nears the concrete sidewalk below. So she's moving down, she's slowing down, so her acceleration vector is up. The other question, number 10. The diagram at the right portrays a Hot Wheels track designed for a fun physics lab. The car starts at point A, descends the hill, continually speeding up from A to B. After a short straight section of track, the car rounds a curve and finishes its run at point C. The car continuously slows down from point B to C. Using this information, complete the following table. So at point X, direction of the velocity vector, where it's moving over this way, it's moving to the right, okay? And it's because the direction of the velocity is always in the direction of motion. At Y, it's also moving to the right because that's the direction it's moving. And the direction of the velocity vector at Z is to the left. Again, for the same reason. At X, it is moving to the right, and it tells us that it is speeding up. So that means that it is moving to the right, speeding up. The acceleration vector is in the same direction, so it's also to the right. At Y, the car is moving to the right, but it says it is slowing down. So that means that the direction of the acceleration vector is to the left because it is moving to the right and slowing down. And then for Z, it is moving to the left and it is slowing down. So that means its acceleration vector is going to the right. Sorry about that. I have a new computer or a different computer, and the page down button is in a different spot, and so it always returns to home. Okay, so questions from the book. You had questions 9 through 12. So the answers are, for number 9, what was the acceleration of a car moving along a straight road that increases its speed from 0 to 100 kilometers per hour in 10 seconds? And the acceleration is 100 minus 0 divided by 10, which gives you 10 kilometers per hour per second. Number 10, what is the acceleration of a car that maintains a constant velocity of 100 kilometers per hour for 10 seconds? It's 0 because the velocity doesn't change. And it asks you, why do some of your classmates who correctly answer the preceding question get this wrong? Well, it's partially because they're just plugging in numbers and they didn't stop to think about the fact that it said constant velocity. If it's constant velocity, there's no acceleration. Number 11. When are you most aware of your motion in a moving vehicle? When it is moving steadily in a straight line or when it's accelerating? And if you were in a car that moved with absolutely constant velocity, no bumps at all, would you be aware of motion? So you're aware of changes in your speed, but not steady motion. Therefore, you're aware of acceleration, but not constant velocity. So you can feel it when things speed up, just like if you were on a roller coaster and the car sped up very quickly. And same thing in a vehicle. But if things are moving along just constantly, you would not be aware unless you started looking outside. Number 12, acceleration is generally defined as the time rate of change of velocity. When can it be defined as the time rate of change in speed. It can be the time rate change in speed if you're going in a straight line. Right. So what we're going to work on now is a number of questions in your packet. This is page 11. So is it possible to have acceleration when the velocity is 0? If no, explain. What do you think? No, because acceleration is a change in velocity. If the object's not moving, there can't be any change in velocity. Number 2, is it possible to have an eastward velocity with a westward acceleration? If no, explain why not. And if yes, give an example. Well, what do you think? So yeah, if something's moving east but slowing down, the acceleration vector is directed west. And we've had a number of examples very similar to that. Number 3, a flock of robins is migrating southward. Describe the flock's motion at instants when its acceleration is A, positive, B, negative, and C, 0. Take the southward direction as positive. So let's take part A first. So if south is positive and the flock is moving south, then the acceleration, if it's positive, it's speeding up and the acceleration vector is directed south. If the acceleration is negative, it means they're slowing down. And if it's 0, it means that they're moving at constant speed in a straight line. Number 4, a track runner starting from rest reaches a velocity of 9.3 meters per second forward in 3.9 seconds. Determine the runner's average acceleration. So we want to be sure we use the equation properly. So if it starts from rest, its initial velocity is 0. Its final velocity is 9.3. And the time is 3.9 seconds. So I've got final minus initial divided by time. So 9.3 meters per second divided by 3.9 seconds, you end up with 2.4 meters per second squared. And it's still forward. Please be sure you carry on the direction. The Renault Espace is a production car that can go from rest to 26.7 meters per second with an incredibly large average acceleration of magnitude 9.52 meters per second squared. How long does the Espace take to achieve its speed of 26.7 meters per second? So in this case, they want us to solve for time. So we need the equation that we rearranged to solve for time earlier. So time is VF minus VI over A. So the initial velocity is 0. The final velocity is 26.7 meters per second forward. And the acceleration was 9.52 meters per second squared. So when we plug everything into the equation, we end up with 0.284 seconds. That's really fast. Number 6. A motorcyclist traveling at 23 meters per second north applies the brakes, producing an average acceleration of 7.2 meters per second squared south. What is the motorcyclist's velocity after 2.5 seconds? So we need our final velocity equation. So the initial velocity was 23 meters per second north. The acceleration was 7.2 meters per second south. And the time is 2.5 seconds. So when we are doing this, we have to recognize that if we're going to say north is positive, south has to be negative, which means that since this thing is slowing down, the velocity is going to get lower and lower. So when we plug in the acceleration into the equation here, it's got to be negative. So I'd like setting north is positive and south is negative. So we've got final velocity equals negative 7.2 meters per second squared north times 2.5 seconds plus 23 meters per second. And that gives us 5 meters per second north. Take a moment to be sure that you make a note that you understand that and that it makes sense. Number 7, an arrow strikes a target in an archery tournament. The arrow undergoes an average acceleration of 1.37 times 10 to the third meters per second squared west in 3.12 times 10 to the minus second seconds, then stops. Determine the velocity of the arrow when it hits the target. So again, we're going to use our same equation, but this time we want to solve for our velocity. So we've got our v final is going to be 0. Our acceleration is what was given. The time is this really small number. So vi equals vf minus at. Remember that because it's having this, that negative west is the same as meaning east. So our initial velocity, once we plug this all in, ends up being 42.7 meters per second east. All right. So now you are ready for 2 mop-ups. So KC4 is on acceleration concepts. It's the idea of whether it's rightward or northward and what happens when you're speeding up and slowing down. And do you have acceleration when you're at constant velocity? And the other one is pure math. It's plugging numbers in and calculating your accelerations. So that is what I'm going to leave you with to work on. Good luck on those. Be sure that if you have any questions, you ask classmates or the juniors or email me. And one good resource to get assistance is going to Physics Classroom with their lesson about acceleration. They have some interactives and things on their website that's very helpful. Your physics textbook definitely talks about acceleration, but doesn't go into as much detail as some of this. But feel free to email me if you have any questions. Good luck.